Good morning. I welcome you all to this session of fluid mechanics. Now, last class we were discussing a problem which we could not complete. So, today first we should complete the problem, the latter part of the problem, and then we will proceed to a new topic of this section. So, if you look to the problem which we were discussing last class, please see a paddle wheel of 100 millimeter diameter rotates at 150 rpm. I think this problem was taken well in last class, just I am repeating it again. Inside a closed concentric vertical cylinder of 300 millimeter diameter, completely filled with water. Assuming a two-dimensional flow in a horizontal plane, find the difference in pressure between the cylinder surface and the center of the wheel. If provision is made for an outward radial flow which has a velocity of 1 meter per second at the periphery of the wheel, what is the resultant velocity at a radius of 100 millimeter? So, the last part we could not complete. If the provision is made for an outward radial flow, this one which has a velocity of 1 meter per second at the periphery of the wheel, what is the resultant velocity at a radius of 100 millimeter? This is the question. So, first part we did, if we recall, the first part was very simple. It is like this, which we did first part, that like this is the cylinder and this is the paddle wheel, this is the axis. So, we recall that there are two in a plane, in a horizontal plane. If we see, let this point is center 0, this is 1, and at the same radial location we take another point 2, that is at the surface, and this one we define to be radius r1 and this is the radius r2, that is the radius of the cylinder. That means if we see the plan view, we will get this type of thing. That means this one with this paddle wheel, this is like this. So, this is the center one, this is the radius at radial location. So, what we did, we assume from 0 to 1, that means within this domain the flow is force vortex, and from 1 to 2 flow is free vortex. So, we found out the rotational speed omega. Omega is 150 rpm, that means 2 pi into 150 by 60, which was found yesterday. This comes out to be, well, this value comes out to be something 15.705 radian per second. So, we can find out this, repeating again, P2 minus PO by rho, or P2 minus PO, first you write this one, is nothing but P2 minus P1 plus P1 minus PO. So, this part is found from the free vortex pressure distribution equation, because this part is free vortex zone and this part is forced vortex zone, core forced vortex. Alright, this is the forced vortex zone. This is the free vortex zone, this is the forced vortex zone. So, this part is found out from the forced vortex zone. Okay? So, this we solve. P1 is equal to P1 minus P0 from the forced vortex equation, omega square by 2 into rho into R1 square minus 0. That means simply R1 square. And value of R1 is given as 0.05. If you put it, we will get the value of P1 minus P0. Similarly, P2 minus P1 we will get from the Bernoulli's equation at rho by 2 V theta 1 square minus V theta 2 square. V theta 1 is omega into R1, R1 with 0.05 and omega with this. If you calculate V theta 1, that means at this radius, this will be V theta will be 0.785 meter per second, 0.785 meter per second. So, you can very well find out V theta 2 considering the free vortex motion from 1 to 2. You know that for free vortex motion, V theta is C by R. That means V theta into R is constant. Therefore, V theta 2 is 0.785 into its radius 0.05, that means this one, divided by, at this point we want the velocity, so this radius, which is 0.1. That means simply it is half of this. which becomes is equal to 0.392 meter per second. So with this value of V theta 2 and this value of V theta 1, we can find out P2 minus P1. So if you find out P2 minus P1 and then you find out the difference in pressure, which becomes equal to P1 minus P0 becomes equal to 0.583 kilonewton per meter square. There is no problem. Now next part is the pressure. Now how to find out pressure, how to find out the velocity. Next part is the radial velocity. Now if there is a radial velocity, that means if there is a radial velocity, that means you draw the radius, that means if there is a radial velocity coming out, if there is a radial velocity along with the tangential velocities are there in this direction. So along with the tangential velocity there is the radial velocity. Now radial velocity, if it is there, now we will have to find out that what is the functional relationship of radial velocity. Whether it is a function of r only or theta only or general function of r theta. So we will have to first find out the explicit form of the radial velocity with the independent variable, that is spatial coordinate r theta. So to do this, we will have to explore the continuity equation. Now for a two-dimensional steady flow, the continuity equation del Vr, for an incompressible flow del Vr del r, for an incompressible flow, two-dimensional incompressible flow, the continuity equation Vr by r, if you recall, 1 by r del V theta del theta is equal to 0. Alright. So therefore, we see that del V theta del theta is 0 because already we have found that V theta is a function of r only. So V theta is not a function of theta. So this is 0. So therefore, continuity equation tells us del Vr del r plus Vr by r is 0, which can be written as, now del I write in terms of d. So if you take 1 by r d dr of, because Vr is a function of r only, from here we see d dr of Vr into r is equal to 0. So which tells that Vr, alright, so which tells that Vr is equal to some constant, let k by r, that Vr into r is equal to constant. So from the continuity we see that the dependence of Vr is that Vr is equal to some constant divided by r, alright. So therefore, from here, from the equation of continuity we find out that Vr is equal to constant by r. So therefore, now next job is very simple. It is given that the outward radial flow velocity is 1 meter per second at the periphery of the wheel. That means this point, the radial velocity is 1 meter per second, that is this point. So we can find out the k. Rather, we can straight away find out the radial velocity at a point here, which is 100 millimeter in diameter. Let this point is the 100 millimeter in diameter, point in question. Let this is 3 point. And this R3, that means this one, R3 is equal to 100 millimeter, that means 0.1 meter. So therefore V3, that means at this point 3, VR3 is equal to, it is inversely proportional to r, that means it will be the radial velocity 1 meter per second corresponding radius, which is 0.05 divided by the R3 is 0.1. So what is the value of VR3? VR3 value is 0.5, very good, meter per second. In the similar way, we can find out the value of V theta, that means if I write this V theta 3 is equal to, what I can write, now again you see that V theta 3 we can equate with 1, V theta 1 is known, so V theta 1, so V theta 1, what is the value of V theta 1? V theta 1 value we have found out, V theta 1 is 0.785, which is the velocity here. Well, so 0.785 into the radius, it is also inversely proportional to radius, that means 0.05, divided by the radius of the 0.3, that means 0.1. That means this is also V theta 3, it is alright, the radius is 0.1. So this is also half, 0.392 meter per second, alright, 0.05 by 0.1, so 0.392. But here probably I have done a mistake, so it is not 0.1. This is V theta 2, this diameter is Well, 300 millimeter, 0.15. Well, so this diameter, this value is, you please cut 5 point. What is this value? 2. No, I am sorry, I am very sorry. What will be this value? 0.26 to calculate it. It is wrong because it will be 0.5 because here the radius is 0.5. Well, here the radius is 0.5. So 0.15. Radius is 0.15. 300 millimeter diameter. So radius is 0.15. So that's why this is 0.392. Now the radius is 0.1. So therefore we know VR3, we know V theta 3. So the resultant velocity V is root over of VR3 square plus V theta 3 square. And if we want, that means this value becomes 0.636 meter. Very simple. That means here at this point, this is the radial velocity. Let this be the direction of rotation as it is shown. This is the direction of, so that means this is the tangential direction that is perpendicular to one. So this is the V. All right. So its inclination with radial direction, if it is theta, then tan theta will be what? Tan theta will be V theta by VR. So with the radial location, if theta is the angle, then theta is tan inverse V theta by VR. V theta by VR, and you find out theta to be 38 degree. If you find out that V theta by VR. All right. So this is the problem which we could not complete in the last class because of time. Now today I will start another topic of this section is a hydraulic siphon. So before I start the hydraulic siphon, it is a very simple thing which is a practical device and which can be analyzed simply by the application of Bernoulli's equation. But before that, I like to tell you a few words which is very important in this context, that whenever the fluid flows in case of an ideal flow, now if we consider this like this, that in any fluid circuit or flowing device, if we exclude the energy interactions from outside, that means no energy is added from outside to the flow of fluid or no energy is taken from the flow of fluid. It is not the case for flow of fluid through a turbine where the flow takes place to the turbine. If you consider turbine as a device, work is taken out because work is developed by the turbine. Or in case of a compressor or pump, when the fluid flows through the device like pump and compressor, work is given in. So if you exclude this type of devices, only we consider the flow of fluid in certain device or in certain equipment or in a pipe or whatever may be. That means if the fluid flow situations exclude these circumstances where the work interactions from the outside source, then we can tell like that if the fluid is inviscid, then the total mechanical energy remains constant in the flow during the flow. Obviously, total mechanical energy is constant in the entire flow. It comes, no equation, nothing comes from very simple concept of conservation of energy. And total mechanical energy why remains constant? Because if the fluid is inviscid, mechanical energy cannot be dissipated into other form of energy, because it is the viscosity or the fluid friction which causes the conversion of mechanical energy, a part of the mechanical energy which we call as dissipation of energy, that means conversion of a part of mechanical energy into intermolecular energy or heat. So that part is absent. So therefore total mechanical energy remains constant. So there may be a conversion from one form to other form, that pressure energy to kinetic energy to pressure energy, potential energy to kinetic energy, pressure energy to potential energy, but some of these three components of energy remain constant. That is number one. Number two, now in practice, fluid is not ideal or inviscid. All fluid has got viscosity. So therefore, practically all fluids which we can think of in practice are viscous fluids, and they are known as real fluids. So therefore, real fluids is a synonymous term of the viscous fluid. So now in practice, the mechanical energy changes. Why? This is because there is a dissipation of mechanical energy due to friction into intermolecular energy. Now, just consider this, that whenever there is a flow of ideal fluid from one point to other point, the mechanical energy remains constant. So therefore, the flow is equally possible in both the directions, and flow is maintained by virtue of its inertia. Okay? Now, or it may be by virtue of its inertia or maybe some external forces acting on the fluid. Now, in case of a real fluid flow, you have to understand this, whenever there is a flow of fluid, so energy at the upstream section or a upstream point is more than that at the downstream point, which means that fluid flow by virtue of the energy gradient. So energy is the potential which causes the fluid to flow. If you compare with other phenomenological facts like flow of heat, heat flows from a higher temperature to lower temperature. Electricity flows from higher potential to lower potential. So therefore fluid flows from higher energy to lower energy. Now in reality, for real fluid, the fluid flows from higher energy to lower energy, and this difference of energy is consumed by the fluid friction or the viscosity. That means this is the energy, mechanical energy, which we call as a loss. You have seen that in Bernoulli's equation we call this difference of energy the loss of energy. Loss of energy from the viewpoint of mechanical energy, because energy can never be lost. That means this difference, that means upstream is higher mechanical energy, downstream is lower mechanical energy. So this difference of mechanical energy is dissipated or converted into the form of intermolecular energy. That is loss from the viewpoint of mechanical energy. That is the loss in mechanical energy. That's we call it in terms of loss in fluid mechanics. So this loss of energy is consumed by the friction, that is due to friction. Now in this context you will see that sometimes we see that in upstream part of the fluid the pressure may be low, downstream part the pressure may be high. So apparently it gives a confusion, the fluid is flowing from a low pressure to high pressure, doesn't matter. Fluid is obviously flowing from high energy to low energy. That means upstream, though the pressure is low, you may see the kinetic energy, the velocity is such, the data made is such that the sum of the kinetic and potential energy can counterweigh or counterweighs the difference in pressure energy and makes the sum of the three components definitely more than that of the downstream. Sometimes we may be confused seeing that water spontaneously goes from a lower elevation head to higher elevation head. How it is going from a lower potential energy to higher potential energy? It's not the potential energy, it's total mechanical energy. That means at the lower potential energy, probably the velocity energy, that is the kinetic energy or the pressure energy, as such that the sum of the three components, the total mechanical energy is more than that of the downstream part. So therefore fluid always flows from higher mechanical energy to lower mechanical. It is a very simple thing, but still you should have mind so that you should not have any confusion apparently as you see. So pressure, fluid can flow from a low pressure to high pressure, from a low head to high head, provided the energy at the upstream portion is higher than that of the downstream portion. It always flows from a higher to a lower energy level. Now we come to the hydraulic siphon. A hydraulic siphon is a device which raises the liquid from a level where its pressure is atmospheric by a tube, and it does so provided a negative pressure or a vacuum pressure in the tube is caused. Otherwise fluid from an atmospheric pressure cannot go up. How it will go up? From the energy conservation, its pressure has to be lower than the atmospheric pressure. So creating a vacuum pressure, raising the fluid from a level where the pressure is atmospheric pressure is known as the siphonic action. Is known as a siphonic action, and the tube or instrument or the device, whatever you call, does it is known as a hydraulic siphon. So let us now concentrate to a hydraulic siphon. How does it work? Now let us hydraulic siphon. Hydraulic siphon. Very simple, you have read it probably at your school level, but still again brushing up. Let us consider the two tanks. Oh sorry, this will be difficult. Now hydraulic siphon. Hydraulic siphon. Let us consider tube like this. Well, let us consider this one. Let us let us consider a situation like this. This is a hydraulic siphon. Let us consider two tanks. One is T1, another is T2. So T1 tank, the water is at a higher elevation than the water level than the tank T2. Let this point is B. Let this point is B. where this is discharging. So, this is discharging that at this point B, right at this point B, and let this point is A, free surface. A has a elevation at ZA, B has a elevation at ZB. Well, ZA is greater than ZB, obviously it is shown from the figure. Now what happens? Definitely the liquid level here is at a higher energy than the liquid level here, because pressure energy and kinetic energies are 0. So, the elevation energy or the potential energy is higher than this. So, if we fill up a tube like this, a U tube, inverted U tube, with the same liquid and dip this tube into this tank, then water will automatically flow, because what we are doing practically, we are connecting this water of the two tanks by a water circuit. That means full of water in a pipe and you just connect it. So, what will happen, since there is a energy difference between A to B, the water will go on flowing like this from A to B. So, therefore, if we consider the point A and B, very simple, because I am telling you, if you can understand the thing physically, then equations are very simple. So, A to B, there is every possibility water should come from A to B. But while we consider the flow in this part, we may be apparently confused that how the liquid is going from this tube at this point at a lower potential energy to higher potential energy, then means definitely the pressure created is lower at this point, such a way that the sum of the three components of the energy at any point must be lower than the sum of the three components of energy at this point on this point. That is why the flow in this part is possible. So, as a whole, if you consider the flow with the entire circuit, flow from this point to this point is very much possible. So, now this is the siphonic action. So, if you consider the phenomena, the action, that liquid is flowing out of this tube, and if you continue it, the entire liquid will be coming out. That means this tank will be emptied, so that the all liquid in the tank can go to the tank T2 from T1 to T2. So, physically there is no bar, or it is totally possible from the physical point of view. Now, let us write the Bernoulli's equation between point A and point B. So, Bernoulli's equation between point A is, if I write Pa by rho plus, what is the velocity here? Velocity here is 0 at the free surface, the velocity here is 0, though this surface is going down, but it is very slow, or we can maintain a constant head by supplying, we can study and analyze this with a maintaining a constant. So, there is no movement of this surface, so velocity energy is 0. Or even if there is a movement, this velocity is very small because of the large cross-sectional area of the tank. So, the most important is the elevation head. This ZA is its elevation referred to any vertical, referred to any reference datum from which this elevation head is ZB. Let us then, very important is that we consider this as delta Z, that means this difference between the elevation head of these two, delta Z. Now, therefore, this can we write Pa by rho plus 0 plus GZA is equal to Pb by rho plus 0 plus GZB. So, Pa is equal to Pb is equal to P atmospheric, P atmospheric. So, this is the 2 atmospheric pressure. So, it is very simple that if we write this B point not here, so otherwise it will give you a confusion. So, GZA minus ZB, what is happening? So, I am sorry, this, because you can argue that if I write this, this is a confusion, this I will explain it afterward, there is a loss, exit loss. So, exactly at the exit plane if you consider, which is the atmospheric pressure, that means the exit is taking place just at the surface, I have drawn like this. So, there is no pressure difference between this point and this point. That means you can consider exit just at the free surface or just below the free surface. So, the pressure is same as the free surface, atmospheric pressure. So, I am sorry. So, here there will be Vb square by 2, Vb square by 2. So, if you take Pa and Pb as the same as the atmospheric pressure, they cancels out. So, simple deduction is that Vb is equal to 2G delta Z. I will explain this afterwards if one is interested to know if exactly at the free surface after the liquid comes to rest, if I write, then Pa, Pb cancels out, how the difference of this ZA, ZB energy goes, that comes out to the exit loss. That means the velocity energy which is discharged here, that is being dissipated through the friction into intermolecular energy, that is known as the exit loss. So, a loss term will come, that I will consider afterward. Now, for inviscid flow, if there is no loss, if we don't count any loss, so through this path of flow, if we write the energy equation at the point A at the free surface and the discharge plane point B, then I get that Vb is equal to root over 2g delta z, which is very simple. That means the kinetic energy created here by virtue of the elevation difference delta z. That means the elevation head of A above B is utilized in creating this velocity Vb. Now we see that how the flow is taking place in this vertical section of the pipe. Let us consider a point C whose elevation is Zc, and let this height is h. Zc is the elevation measured from the same datum from which the elevation of A is Za, the elevation of B, rather B point is here, elevation of B is Zb, like this. So now if we write the Bernoulli's equation from this point A, which is at free surface, and point C, this point A and point C, what we can write? Please tell me. We can write that Pa by rho, here the velocity is 0, plus Gza is equal to Pc by rho plus the velocity at the point C, Vc square. I have to write in the same page, that is why this is superimposed, otherwise I cannot get the figure. Vc square by 2 plus, you tell me, Zc, Gzc. So therefore, Pc by rho is Pa by rho, very simple, minus Vc square by 2 minus Zc minus Za, that means H, which means the pressure at C has to be lower from the pressure at A by the amount of Vc square by 2 and Gh, which physically signifies, now this is for an incompressible, this is for an ideal flow. Flow is incompressible and ideal. That means the total energy at this point and this point remains same. So what happens? A part of the pressure energy at Pa is being utilized to create the kinetic energy and the datum energy or the potential energy, so that the pressure energy at C has to be lower than that of A by these two amount, kinetic energy and the potential energy. So if pressure at A is atmospheric, that means Pa is atmospheric pressure, as we have already written. Therefore the point Pc, the pressure at Pc is lower than the atmospheric pressure by this amount, Vc square by 2 plus Gh, minus minus. So therefore the pressure is vacuum pressure. Now you see, if we consider the losses, what will happen? Now if I consider the losses, again better we draw this figure. If we consider the losses, now what will happen? If we consider the losses, that means, in a short, I am drawing this, again the siphon, okay, this is not like this, let this goes like this, this is the discharge plane, this is the discharge plane B. Let us do like this, this is the point A, okay. Now this is the point C, so this was the point A, this is the point B, so this is ZB, again this is ZA, so this is delta Z, this is delta Z, and this is H, and this is ZC. Now we have found out that Vb is root over 2g delta Z, very simple. That means this potential head is utilized to create the kinetic energy, writing the Bernoulli's equation between these 2 points. Now if we consider a loss, frictional loss, that if we consider a real fluid, we have discussed earlier, the Bernoulli's equation can be used for a real fluid with a modification term as loss. That means if we write the Bernoulli's equation between A to B through this fluid path, that is the fluid path, taking care of the frictional loss of energy, then we can write the total energy at the upstream point, that means Pa by rho plus Gza is the total energy at the downstream point. I have told that the upstream point energy will be more than the downstream point by the loss term. Therefore total energy from at the downstream point, Vb square by 2 plus Gzb plus a loss term HL, that is the loss of energy due to friction per unit mass, because these are the energy quantities per unit mass. This is known as the frictional head loss. So frictional energy loss, HL. So in that case, if you cancel PA and PB to be equal to the atmospheric pressure, then you get simply the VB is equal to root over 2G delta Z. Okay. So this will be the head loss term. So if this is the energy loss, usually energy loss is written in terms of the per unit weight. This is the nomenclature, we write GHL. That means HL is the frictional head loss, that is the energy loss due to friction per unit weight. That is why I multiplied with the G, so that GHL becomes the energy loss per unit mass due to friction, because H is usually usually used to express the frictional loss per unit weight, that is the head whose dimension is meter. So therefore it is GHL, that means 2G delta Z minus HL. It is very simple. It comes from this. So VB is equal to G ZA minus ZB minus GHL. That means the velocity created is less than 2G delta Z, but that means the potential head is effectively reduced by the amount HL. That means the velocity which will be generated in this case will be less than this one, which is generated because of the ideal fluid. So therefore due to the friction, some part of the mechanical energy is dissipated or converted into intermolecular energy, which is taken care of by this loss term, so that the velocity head is generated at the discharge plane is less than that could have been generated by the ideal flow. Now if you write the equation here and here considering the loss term, and if you consider the loss frictional energy loss per unit weight or loss of head due to friction per unit weight is HL dash, that is between A to C, then I can write again the same equation which we wrote earlier, PA by rho plus here VA square, that is 0, GZA is equal to, here if we write PC by rho plus VC square by 2 plus GZC. So this energy is to be more than this by the loss HL dash. That means now I see that PC by rho has to be less than PA by rho by which amount? VC square by 2 plus PA by rho is VC square by 2 plus G into H, because ZC minus ZA is H plus HL. So you see PC by rho has to be lower than the PA by rho, that means the pressure here is lower by these 3 amounts, which means a part of the pressure energy here is responsible for creating the kinetic energy here, increasing the potential energy here, plus to overcome the friction. That means this pressure has to be sufficiently low as compared to this point, because to take care of this. Alright? It is very simple. Alright, HL dash, sorry, here I have considered. Okay? G, sorry, GHL dash. This is the question of consistency with the unit. So concept is clear. Now therefore we can justify that the flow of fluid in the liquid through the siphonic tube or the siphon, that this part the pressure is minimum and then gradually it becomes increases and becomes again atmospheric. So which point the pressure will be the minimum one? So topmost point, because the pressure will go on decreasing. Now VC square by 2, now this VC and this VB is same if we consider the pipe to be of uniform diameter. Let us consider a point D at the topmost point here, D. Let us consider where the datum head is ZD. You write the Bernoulli's equation now. You write the Bernoulli's equation between this point and this point, taking care of the losses. First of all, you neglect the loss, because usually the losses are, just I have explained what is the role of the losses, but frictional losses are low because the velocities are very low. So therefore you can neglect the losses. Neglecting the losses, if you find out this pressure, so what will be this pressure? PD by rho is equal to, tell me, PA by rho minus VC square by 2 minus G, let this height is H1, any height you take. So VD square, VC and VD is same, okay, VD square, very good, minus GH1, alright. Now if we consider the pipe to be uniform, so VD is VC and VB, so we can write VD is equal to Vb. So Vd square is 2G delta Z. Alright, very simple. So Pd by rho is equal to Pa by rho minus what is that? 2G delta Z. So Vd square is 2G delta Z. So Vd square by 2 is G delta Z and Pa by rho minus G. So minus G H1 plus delta Z. That means it is the total height. Let this height is big H. In the same, the space is so limited space, so it is very difficult, all these superimpose G into H. That means minus GH. So just bracket is not needed, minus GH. That means the pressure here is the Pa by rho, that means atmospheric pressure minus GH. The same equation you can derive if you write the Bernoulli's equation between this point and this point. You can find out the same equation. So therefore this is the minimum pressure. Obviously the minimum pressure will occur here, that is at the topmost part of the tube where the vertical height will be maximum. So this pressure Pd is equal to Pa by rho minus the total height from this level of liquid H to the uppermost point minus GH, neglecting the losses. If you make the loss, then this pressure will be this minus GH minus the loss which has taken place during this part of the flow, frictional losses. Properly take into account minus GHL1 or HL2, whatever you define. So alright, okay, alright, it's very simple. Now in this context, I like to tell you one very important information of fluid flow, which is very important for designing any practical equipment. Now first you see that in this type of situation, if this is open to atmosphere, this surface, so this point are having pressure below the atmospheric pressure. Alright, as you go up, you see pressure is becoming lower and lower, that is lower and lower than the atmosphere, then vacuum pressure is increasing. Obviously, now if you go on increasing the height, the vacuum pressure will be increasing, then the pressure is still going to be lower and lower. What is the restriction of the minimum pressure? Can you tell me what is the restriction? So physically it is alright, we can make a very high tube and we can make the flow possible. Theoretically, the pressure at any point here, if you go up, will be lower than the atmospheric pressure by this potential head and the kinetic energy created. If we take a very small tube, so kinetic energy will be very high. So under all situations, the physical definition is alright, but is there any limitations of the minimum pressure? The minimum pressure in this circuit is at here. What is that limitation? Can you tell me what is the limitation? This limitation is that that pressure, vacuum pressure, or the pressure created should not fall to below a pressure which is the vapor pressure to the of the liquid at the existing temperature. What will happen? Then the liquid will boil up. So vapor will be generated. So therefore the limit to this pressure, the minimum pressure, is the vapor pressure of the liquid at the existing temperature. So liquid will start boiling up, and the phenomena is known as cavitation. Cavitation. Now I define you the cavitation in general. This phenomena is known as cavitation. So liquid will boil up and the hydraulic circuit is closed. Hydraulic circuit is detached. So fluid flow is stopped. This phenomena is known as cavitation. Now I define you in general what is cavitation. Cavitation is like that if in any hydraulic circuit, the liquid circuit, at any point if the pressure is below the atmospheric pressure, so when one has to be very careful that this pressure should not go below the vapor pressure of the liquid at the existing temperature, where the liquid will start boiling up. So liquid will change its phase and the flow will be stopped. You know that for all liquid, there is a pair of pressure and temperature at which it changes its phase from liquid to gas. Now let us consider the water. We know at ambient pressure, the water boils up at 100 degrees Celsius. But at the ambient temperature also water boils up. For consider today's ambient temperature as 20 degrees Celsius. At 20 degrees Celsius, water also boils up. We don't have to heat the water. If we reduce the pressure to a subatmospheric pressure, which is equal to the saturation pressure corresponding to that temperature that you have read in the physics. For example, it may be 0.3 atmospheric pressure, where 20 degrees Celsius is the boiling point of water. That means that is the saturation pressure corresponding to that temperature. That pressure is known as the vapor pressure of water at its existing temperature, where the water will boil up. So by chance, the room temperature water has a pressure of that value, then water will start boiling up. So therefore, one has to take care of that this vapor pressure at the existing temperature should be the minimum pressure, so that the pressure at any point in the hydraulic circuit should be above that to avoid the phenomena of boiling of the liquid. What happens in practice, when this pressure is approached, the liquid starts boiling and the vapor pockets are generated. And therefore, what happens, these vapor pockets ultimately is generated and it is carried away by the liquid and then immediately collapse when it reaches a higher pressure region of high pressure, and liquid particles from surrounding rushes to fill up the cavities, the cavities are formed, and this causes a serious damage to the surface of the duct through which the liquid is flowing, or the surface of the body past which the liquid flows, and causes a serious damage, and immediately the flow is stopped because of the vapor locking. So this phenomena is known as the cavitation. So therefore, in any hydraulic circuit, design of hydraulic circuit where there is a chance of having a pressure lower than the atmospheric pressure, one has to take care in designing the circuit that that pressure should be much above, with some allowances above than the vapor pressure of the liquid at the working temperature. Okay, thank you.